Every second, millions of independent routers pass data across the internet without a central controller to dictate the path. Each device must determine for itself how to move traffic through a complex, ever-changing topology. Early networks used distance vector routing, where a router only knows the directions provided by its immediate neighbors. This method limits a device's visibility to the hops directly in front of it. Link state routing offers a different model. Every router in the network collaborates to maintain an identical, complete map of the entire topology. As shown in this hierarchy of interior gateway protocols, Open Shortest Path First, or OSPF, is the primary example of a link state algorithm used in enterprise environments. In an OSPF environment, each router independently calculates its own optimal paths using a shared, synchronized structure known as the Link State Database, or LSDB. By synchronizing this data across every node, the protocol attempts to replace individual routing assumptions with a single, verified map of the network. To see how this map is constructed, we need to trace the process from the moment a router discovers its neighbors to the calculation of the final paths and the architecture required to scale the network. The first requirement is neighbor discovery. A router must identify which other OSPF-enabled devices are physically connected to its active interfaces. These routers then exchange link state advertisements, or LSAs. These are the discrete units of data used to assemble the network map. Each LSA contains specific details regarding the router's local interfaces, its connected subnets, and the current operational state of those links. If these LSAs are not successfully shared and synchronized across the topology, the database cannot form. This makes establishing a neighbor adjacency the critical first step in OSPF operations. OSPF uses a hello packet as a multicast heartbeat sent to the address 224.0.0.5. This packet allows routers to dynamically find one another on a shared segment. Looking at the connection between router 1 and router 2, we can see the specific sequence of states required to build an adjacency. A router begins in the down state. When it receives a hello packet from a neighbor, it transitions to the init state. The two-way state is reached once a router sees its own router ID reflected back in a neighbor's hello packet, confirming that communication is bidirectional. In the exchange state, routers trade database descriptors. These high-level summaries of their LSAs allow each router to identify which map pieces are currently missing. Finally, routers reach the full state. This occurs only after they have requested, updated, and acknowledged every missing LSA, resulting in identical link state databases. This progression ensures that routers reach a point of data synchronization before they are allowed to use the topology to route traffic. On a shared segment with multiple routers, a full mesh exchange creates high volumes of redundant traffic as devices attempt simultaneous updates. OSPF manages this by electing a designated router, DR, and backup designated router, BDR. Standard routers on the segment, known as DR others, only form a full adjacency with the DR and MEDR. These DR others remain in a two-way state with each other. They acknowledge neighbors but do not exchange raw LSA updates directly, preventing redundant flooding. The election follows a hierarchy. The router with the highest OSPF priority wins, with the highest router ID serving as a tiebreaker. On point-to-point connections, such as a direct serial link, this mechanism allows OSPF to scale on local Ethernet segments by centralizing the synchronization process. Once the database is synchronized, each router runs Dijkstra's Shortest Path First, or SPF, algorithm to find the best path to every destination. The algorithm selects the optimal route based on the lowest cumulative cost. Cost equals reference bandwidth divided by interface bandwidth. The default 100 megabit reference over a 10 megabit link equals 10, but on modern hardware, 100 megabit, gigabit, and 10 gigabit links all receive a cost of 1, since OSPF rounds decimals up to 1. The algorithm effectively views a 100 megabit connection and a 10 gigabit fiber line as having equal value. To fix this, administrators use the auto-cost reference bandwidth command to raise the baseline above the fastest link speeds in the network. Without this manual calibration, the SPF algorithm cannot accurately differentiate between high-speed paths, leading to suboptimal routing decisions. As a network rapidly expands from a few routers to hundreds, the overall computational requirements for OSPF increase. In a very large network, the SPF algorithm requires significant processing power, and the size of the database can begin to exhaust a router's memory. In a single area design, a change to any individual link forces every router in the network to process new LSAs and rerun the SPF algorithm. To solve this, OSPF uses hierarchical areas centered around a mandatory Area 0, or backbone area. An area is a logical boundary. Routers within share an identical database, but are isolated from topology changes in other areas. For the hierarchy to function, every peripheral area must have a direct connection to the Area 0 backbone. This connection is facilitated by an Area Border Router, or ABR, which bridges the boundary between Area 0 and the peripheral zones. The ABR maintains separate databases for each area it connects to. Instead of flooding every raw LSA across an entire network, it passes summarized routing information between the areas. These areas contain instability. A flapping cable in Area 1 will trigger a recalculation within that zone, but the routers in Area 3 remain unaffected. OSPF routers must also manage traffic going to destinations outside their own domain, such as the Internet. This is the role of the Autonomous System Boundary Router, or ASBR. In this diagram, Router 1 connects the OSPF area to an external network. The ASBR's primary function is to inject external routing information into the OSPF domain, typically in the form of a default route to an ISP. Engineers configure this behavior using the Default Information Originate command on the boundary router. The ASBR connects the internal OSPF topology to external routing environments, allowing traffic to reach destinations across the wider web. OSPF builds its network map through a precise sequence. It begins with hello packets that discover neighbors and move through defined state transitions. Large broadcast domains are stabilized by DR and BDR elections, allowing LSAs to synchronize into a consistent map. Calibrating the reference bandwidth ensures that the SPF algorithm accurately measures path costs across high-speed links. As the network grows, area hierarchies and ABRs protect the system's computational resources. Boundary routers provide the gateway to external networks, completing the topology. OSPF remains a standard in enterprise networking because it provides a scalable, mathematical approach to mapping and routing data across complex environments.